Boiler water condensate corrosion damage mechanisms as a part of uniform or localized loss of thickness. Description of boiler water condensate corrosion based on API 571, general corrosion and pitting in the boiler system and condensate return piping. Boiler water condensate corrosion damage refers to the deterioration of metallic components within boiler systems due to corrosive substances present in the condensate produced from steam. This type of corrosion is particularly concerning in the condensate return lines, heat exchangers, and associated piping systems, where steam converts back into liquid water and may retain impurities and gases. Causes of boiler water condensate corrosion. Number A is dissolved gases. The primary agents contributing to condensate corrosion are dissolved gases, primarily carbon dioxide, CO2, and oxygen, O2. When steam condenses, these gases can dissolve in the water, leading to the formation of weak acids, such as carbonic acid. This lowers the pH of the condensate, creating a highly corrosive environment. Number B, chemical composition. Besides dissolved gases, the presence of contaminants, such as chlorides, sulfates, and other impurities, in the boiler water can exacerbate corrosion problems. These substances can enter the system through feedwater or as a result of leaks. Number C, temperature and pressure conditions. Higher temperatures and pressures in the boiler system can accelerate the corrosion processes by maintaining a greater solubility of harmful gases. Additionally, temperature fluctuations can further promote corrosion activity. Number D, stagnation and flow rates. Areas with stagnant water or low flow rates can create conditions for localized corrosion, as corrosive agents concentrate and aggress upon the metal surfaces. Types of corrosion damage. Number A, uniform corrosion. Characterized by a consistent thinning of the metal across an entire surface, uniform corrosion can lead to gradual failure of pipelines and components. Number B, pitting corrosion. This localized form of corrosion creates small pits on the metal surface, which may not be visible until significant material has been lost, leading to leakage and potential system failure. Number C, galvanic corrosion. When dissimilar metals are in contact within the condensate system, galvanic corrosion can occur, resulting in accelerated corrosion of one metal, the anode, at the expense of the other, the cathode. Number D, stress corrosion cracking, or SCC. Under certain conditions, such as the presence of chlorides, stress corrosion cracking can develop, leading to sudden and catastrophic failures, especially in high-stress areas. Consequences of corrosion damage. Number A, of consequences of corrosion damage is reduced efficiency. Corrosion can cause leaks and failures in the system, resulting in steam loss and a drop in overall efficiency. This can drive up operational costs as more energy is required to maintain performance. Number B, of consequences of corrosion damage is increased maintenance. Regular maintenance and inspections become necessary as corrosion damage progresses, leading to higher operational costs and potential operational downtime. Number C, of consequences of corrosion damage is safety hazards. Severe corrosion can lead to structural failures of key components, posing significant safety risks to personnel and the surrounding environment. Number D, of consequences of corrosion damage is system integrity loss. Thinning of walls and pitting can compromise the integrity of components, increasing the likelihood of catastrophic failures if not addressed in a timely manner. By addressing these factors and utilizing preventive measures, operators can significantly reduce the incidence and impact of boiler water condensate corrosion damage, ensuring safe and efficient boiler operation. Boiler water condensate corrosion affected materials based on API 571, primarily carbon steel, some low alloy steel, some 300 series SS and copper-based alloys. Boiler water condensate corrosion can affect a variety of materials commonly used in boiler systems. The extent and severity of corrosion damage depend on the material properties, environmental conditions, and the specific corrosive agents present. Here are the primary materials affected by boiler water condensate corrosion. Number 1 is carbon steel. Carbon steel susceptibility. Carbon steel is widely used in boiler systems due to its strength and cost-effectiveness. However, it is highly susceptible to uniform corrosion, pitting, and corrosion under insulation when exposed to condensate with low pH and dissolved gases. Carbon steel damage mechanisms. Common failures include thinning of the walls, leaks, and eventual structural failure if not monitored and maintained. Number 2 is stainless steel. Stainless steel susceptibility. Stainless steels are often used for their corrosion resistance, however, they can still suffer from localized corrosion, such as pitting, and stress corrosion cracking, especially in high chloride environments or when subjected to elevated temperatures. Stainless steel damage mechanisms. While generally more resistant, stainless steels can experience pitting corrosion in the presence of chlorides and can also fail under certain mechanical stresses. Number 3 is copper and copper alloys. Copper and copper alloys susceptibility. Copper is commonly used in heat exchangers and fittings but can be vulnerable to corrosion when exposed to acidic conditions. It can also suffer from desinsification when used in brass alloys. Copper and copper alloys damage mechanisms. Corrosion may lead to extensive pitting, especially in water with high CO2 content, resulting in leaks and reduced thermal efficiency. Number 4 is cast iron. Cast iron susceptibility. Cast iron is often used in older boiler systems, but it is susceptible to uniform corrosion when exposed to acidic condensates. Cast iron damage mechanisms. Surface corrosion can lead to flaking, and in severe cases, structural integrity may be compromised. Number 5 is nickel alloys. Nickel alloys susceptibility. Nickel alloys are typically used in high-temperature and high-pressure applications due to their good corrosion resistance. However, they can still be affected by localized corrosion under specific conditions. Nickel alloys damage mechanisms. While resistant to many forms of corrosion, they can face issues like pitting or stress corrosion cracking, especially in environments with chlorides. Number 6 is aluminum. Aluminum susceptibility. Aluminum is sometimes used in heat exchangers, but its susceptibility to corrosion when exposed to acidic conditions, such as those created by condensation, limits its use in boiler systems. Aluminum damage mechanisms. Aluminum can corrode quickly in acidic environments, leading to loss of material, structural weakness, and failure. Number 7 is galvanized steel. Galvanized steel susceptibility. These materials can provide some resistance to corrosion, but when the zinc coating is depleted, the underlying steel becomes vulnerable to corrosion. Galvanized steel damage mechanisms. Once the zinc is compromised, the base metal may experience rapid corrosion, leading to leaks and structural issues. By understanding the materials affected by boiler water condensate corrosion, operators can make informed decisions to enhance system longevity and efficiency, thus minimizing operational risks and costs. Boiler water condensate corrosion critical factors based on API 571. Number A. Corrosion in boiler feedwater and condensate return systems is usually the result of dissolved gases, oxygen and carbon dioxide, which lead to oxygen pitting corrosion and carbonic acid corrosion, respectively. Number B. Critical factors are the concentration of dissolved gas, oxygen and/or carbon dioxide, pH, temperature, quality of the feedwater, and the specific feedwater treating system. Number C. Corrosion protection in the boiler is accomplished by laying down and continuously maintaining a layer of protective Fe3O4, magnetite. Number D. The chemical treatment for scale and deposit control must be adjusted to coordinate with the oxygen scavenger for the specific water service and boiler feedwater treating system. Number E. Ammonia SCC of CuZn alloys can occur due to hydrazine, neutralizing amines, or ammonia-containing compounds. Boiler water condensate corrosion damage is influenced by several critical factors that can accelerate the corrosion process and compromise the integrity of the system. Understanding these factors is essential for effective corrosion management and prevention in boiler systems. Here are the key critical factors of boiler water condensate corrosion damage. Number 1 is chemical composition of the feedwater. Chemical composition of the feedwater dissolved gases, the presence of dissolved oxygen, O2, and carbon dioxide, CO2, in the feedwater can lead to the formation of corrosive acids, e.g., carbonic acid, lowering the pH of the condensate and increasing corrosion rates. Chemical composition of the feedwater impurities, contaminants such as chlorides, sulfates, and other salts can exacerbate corrosion, especially in stainless steel and other alloys. Number 2 is pH level of the condensate. A low pH, acidic conditions, can significantly accelerate corrosion. Maintaining a neutral or slightly alkaline pH in the condensate is crucial for minimizing corrosion damage. Number 3 is temperature and pressure conditions. Higher temperatures can increase the solubility of corrosive gases and accelerate corrosion reactions. Additionally, the pressure within the system influences the phase behavior of water and gases, impacting corrosion dynamics. Number 4 is flow rates and stagnation. Adequate flow rates help ensure the removal of corrosive agents and prevent the accumulation of stagnant water, which fosters localized corrosion, e.g., pitting. Stagnant areas are more prone to corrosion due to the concentration of harmful contaminants. Number 5 is material selection. The choice of materials used in the construction of boiler components plays a significant role in corrosion resistance. Some materials, like carbon steel and certain stainless steels, are more susceptible to corrosion than others, such as high-performance alloys. The presence of dissimilar metals can lead to galvanic corrosion if not properly managed. Number 6 Oxygen scavenging practices. The use of oxygen scavengers, such as hydrazine or sulfite, can effectively reduce dissolved oxygen levels in the boiler water, minimizing the risk of corrosion. However, improper dosing or lack of treatment can lead to increased corrosion rates. Number 7 is condensate return system design. The design of the condensate return system can influence corrosion. Systems with long or intricate piping may trap water and contaminants, increasing the risk of corrosion. Proper slope and drainage design are vital to facilitate effective condensate flow. Number 8 is corrosion inhibitors usage. The application of appropriate corrosion inhibitors can create protective films on metal surfaces, reducing corrosion rates. However, the effectiveness of these inhibitors depends on correct dosing and compatibility with other system components. Number 9 is environmental factors. External environmental conditions, such as humidity and temperature fluctuations, can impact the overall corrosion process. Elevated humidity levels can increase moisture and corrosive species in the environment. Number 10 is operating practices. Regular monitoring and maintenance practices, including regular blowdown of the boiler to remove impurities and control chemical levels, play an important role in managing corrosive environments. Number 11 is deaeration process. The effectiveness of the deaeration process to remove dissolved gases before they enter the boiler significantly influences corrosive potential. An ineffective deaeration system can result in high levels of dissolved oxygen and carbon dioxide in the feedwater. In summary, addressing these critical factors involves implementing a comprehensive water treatment program, regularly inspecting system components, and adopting best practices for maintenance and operation. By understanding and managing these factors, operators can significantly reduce the risk of boiler water condensate corrosion damage, ensuring a safer and more efficient boiler operation. Boiler water condensate corrosion affected units or equipment based on API 571. Corrosion can occur in the external treatment system, deaerating equipment, feedwater lines, pumps, stage heaters and economizers, as well as the steam generation system on both the water and fire sides and the condensate return system. Boiler water condensate corrosion can affect various units and equipment within a boiler system and associated systems. The damage can lead to significant operational issues, including leaks, reduced efficiency, and even equipment failure. Here are the primary units and equipment affected by this type of corrosion. Number 1 is boiler shell and drums. Boiler shell and drums description: the main body of the boiler, including the pressure vessels and drums that contain water and steam. Boiler shell and drums impact: corrosion can lead to thinning of walls, leaks, and failure of the pressure boundary, posing safety risks. Number 2 is heat exchangers. Heat exchangers description, units that transfer heat between two or more fluids, often used for steam generation or heat recovery. Heat exchangers impact, localized corrosion, including pitting and fouling, can occur, leading to decreased efficiency, leaks, and potential failure. Number 3 is condensate return lines. Condensate return lines description, piping systems that return condensed steam back to the boiler. Condensate return lines impact, condensate can introduce corrosive agents, like dissolved gases, into the piping, leading to uniform and localized corrosion, which can result in leaks and maintenance issues. Number 4 is feedwater heaters. Feedwater heaters description, equipment that preheats water before it enters the boiler, improving efficiency. Feedwater heaters impact, corrosion can occur due to the presence of corrosive condensate, impacting heat transfer efficiency and risk of leaks. Number 5 is pumps. Pumps description, devices used to circulate water and condensate in the system. Pumps impact, corrosion can affect pump casings, impellers, and seals, potentially leading to failures, decreased efficiency, and unplanned downtime. Number 6 is steam traps. Steam traps description, devices that allow condensate and non-condensable gases to escape while preventing steam loss. Steam traps impact, corrosion can lead to failure or malfunction of steam traps, allowing steam loss or impairing effective condensate removal. Number 7 is valves. Valves description, components used to control the flow of fluids within the system. Valves impact, corrosion can impair valve operation, leading to leaks, reduced performance, and the need for more frequent maintenance or replacement. Number 8 is insulation. Insulation description, material used to reduce heat loss from piping and equipment. Insulation impact, corrosion can occur beneath insulation, often going unnoticed until severe damage occurs, leading to leaks and insulation failure. Number 9 is auxiliary equipment and piping. Auxiliary equipment and piping description, includes various piping and equipment connected to the boiler, such as economizers, superheaters, and feedwater piping. Auxiliary equipment and piping impact, similar to the main boiler components, auxiliary equipment can suffer from corrosion due to condensate, leading to efficiency losses and risks of failure. Number 10 is supporting structures. Supporting structures description, steel frameworks and supports that hold boiler components in place. Supporting structures impact, corrosion of structural supports can compromise the integrity of the entire boiler installation, posing safety risks. Number 11 is fittings and flanges. Fittings and flanges description, junction points in piping systems and connections in various units. Fittings and flanges impact, corrosion can happen at joints and connections, leading to leaks and the need for repairs. Number 12 Deaerator units. Deaerator units description, equipment used to remove oxygen and other gases from the feedwater to minimize corrosion risks. Deaerator units impact, if the deaerator malfunctions or is ineffective, it can contribute to higher levels of dissolved oxygen in the system, leading to increased corrosion in associated equipment. In conclusion, corrosion caused by boiler water condensate can have widespread effects on various components of boiler systems, leading to increased operational costs, risks of failure, and unscheduled maintenance. Proper water treatment, monitoring of system conditions, and regular maintenance of affected equipment are critical in mitigating the risks associated with corrosion in boiler applications. By addressing these issues proactively, operators can enhance the reliability and efficiency of their boiler systems. Boiler water condensate corrosion appearance or morphology of damage based on API 571, Number A. Corrosion from oxygen tends to be a pitting type damage and can show up anywhere in the system even if only very small quantities break through the scavenging treatment. Oxygen is particularly aggressive in equipment such as closed heaters and economizers where there is a rapid water temperature rise, see Figure 4.82, pits caused by oxygen corrosion. Number B. Corrosion in the condensate return system tends to be due to carbon dioxide, although some oxygen pitting problems can occur if the oxygen scavenging treatment is not working correctly. Carbon dioxide corrosion tends to be a smooth grooving of the pipe wall, see figures 4.83, general metal loss, left end of tube, on steel resulting from oxygen corrosion. The color of hydrous ferric oxide is orange to red-brown. And see figures 4.84, jagged fir tree pattern of corrosion inside a tilted steel pipe caused by condensing steam containing high concentrations of carbon dioxide. The appearance or morphology of boiler water condensate corrosion damage can vary depending on several factors, including the environment, the materials involved, the presence of contaminants, and the specific corrosion mechanisms at play. Below are the common forms of corrosion that can occur and their typical appearances. Number 1 is uniform corrosion. Uniform corrosion appearance. This type of corrosion is characterized by a relatively even loss of material over a large area. The surfaces may appear dull and rough. Uniform corrosion appearance. This type of corrosion is characterized by a relatively even loss of material over a large area. The surfaces may appear dull and rough. Indications. A uniform reduction in thickness can be detected through inspection. The metal surface may show signs of discoloration, and overall, there will be a loss of structural integrity. Number 2 is pitting corrosion. Pitting corrosion appearance. Pitting corrosion results in the formation of small, localized holes or pits on the surface. These pits can vary in size and can penetrate deeply into the metal. Pitting corrosion indications. Pits may appear as small, dark spots that can often be sharp-edged. The presence of rust or corrosion products might be found inside the pits, and surrounding areas may appear normal. Number 3 is localized corrosion. Localized corrosion appearance. Similar to pitting, localized corrosion manifests in small, defined areas rather than uniformly across the surface. This can include forms like crevice corrosion or stress corrosion cracking. Localized corrosion indications. Crevice corrosion usually occurs in tight spaces, such as flanges or pipe fittings, leading to localized surfaces that are heavily corroded while adjacent areas remain fairly intact. Number 4 is galvanic corrosion. Galvanic corrosion appearance. This corrosion occurs when two dissimilar metals are in contact, leading to corrosion of the more anodic material. The affected areas will show uneven wear or corrosion patterns. Galvanic corrosion indications. The coating or surface finish may appear damaged or eroded near the junction of dissimilar metals, often with a distinct contrast in appearance between the affected metal and the surrounding material. Number 5 is rust formation. Rust formation appearance, generally seen as reddish-brown or orange-brown flaky deposits on the surface of corroded steel or iron components, indicating oxidation processes. Rust formation indications. Accumulation of rust can be particularly prominent in areas where water tends to pool or where condensate runoff occurs. Number 6 is erosion corrosion. Erosion corrosion appearance. This type can lead to a rough surface due to the mechanical action of fluid flow combined with corrosion. It may also cause more extensive surface damage. Erosion corrosion indications. In areas of high fluid velocity, you may notice uneven surfaces, grooves, or channels where material has been removed, often accompanied by rust or discoloration. Number 7 is flaking or scaling. Flaking or scaling appearance. This occurs when corrosion products, such as rust scales, detach from the base material, resulting in uneven areas that may feel rough or flaky. Flaking or scaling indications. Affected areas will show signs of peeling, especially in older or poorly maintained systems, where corrosion products build up and then fail, exposing fresh metal underneath. Number 8 is microbiologically influenced corrosion, or MIC. Microbiologically influenced corrosion appearance, caused by bacteria. This type of corrosion may lead to biomasses that adhere to the surface, contributing to localized corrosion features. Microbiologically influenced corrosion indications. Biofilms may present as slimy layers or dark stains, and there may be pits or holes related to microbial activity. In summary, the appearance and morphology of boiler water condensate corrosion damage can provide clues to the underlying causes of corrosion within the system. Regular inspections and monitoring are essential to identify these forms of corrosion early, allowing for timely interventions and maintenance to mitigate the impacts on boiler performance and safety. Identifying the specific type of corrosion and its characteristics can help implement effective prevention and mitigation strategies. Boiler water condensate corrosion prevention and mitigation based on API 571, Number A, oxygen scavenging treatments typically include catalyzed sodium sulfite or hydrazine depending on the system pressure level along with proper mechanical deaerator operation. A residual of the oxygen scavenger is carried into the steam generation system to handle any oxygen ingress past the deaerator. Number B, if the scale/deposit control/magnetite maintenance treatment scheme does not minimize carbon dioxide in the condensate return system, an amine inhibitor treatment might be required. Preventing and mitigating boiler water condensate corrosion is crucial for maintaining the efficiency and longevity of boiler systems. Below are several strategies that can be implemented to address this issue. Number 1 is water treatment. Number A, of water treatment is oxygen scavengers, use chemical additives, such as sodium sulfite or hydrazine, to remove dissolved oxygen from the feedwater, reducing the risk of corrosion. Number B, of water treatment is pH control, maintain the pH of the boiler water within a specific range, typically between 10.5 and 11.5, to reduce corrosive potential. Alkalinity control using caustic soda or other agents can help achieve this. Number C, of water treatment is corrosion inhibitors, implement specific inhibitors, such as amines or phosphates, to form protective films on metal surfaces, reducing corrosion rates. Number D, of water treatment is softening, remove hardness ions, like calcium and magnesium, from the water to minimize scale formation and associated corrosion. Number 2 is deaeration. Number A, of deaeration is deaerator installation, utilize deaerators to effectively remove oxygen and other dissolved gases from the feedwater before it enters the boiler. This is critical for both water quality and corrosion prevention. Number 3 is condensate return treatment. Number A, of condensate return treatment is condensate treatment, ensure that condensate is appropriately treated before being returned to the boiler. This may involve filtration to remove particulates and chemical treatment to address pH and oxygen levels. Number B, of condensate return treatment is use of closed-loop systems, implement closed-loop systems for condensate return, which minimizes exposure to air and, therefore, reduces oxidation and corrosion risks. Number 4 is material selection. Number A, of material selection is corrosion-resistant materials, specify and use materials that have higher resistance to corrosion for critical components, such as stainless steel or alloyed materials in areas prone to condensate contact. Number B, of material selection is coatings and linings, apply protective coatings or linings to vulnerable steel components such as pipes and tank surfaces to prevent direct exposure to corrosive agents. Number 5 is design considerations. Number A, of design considerations is minimize traps and low points, design the system to avoid low points where condensate can pool. Ensure proper slope in piping systems to facilitate drainage. Number B, of design considerations is thermal insulation, use insulation on pipes to prevent condensation from forming on the outer surfaces, which can lead to corrosion. Number 6 is regular inspection and maintenance. Number A, of regular inspection and maintenance is visual inspections, conduct routine visual inspections to identify early signs of corrosion or degradation. Keeping an eye on welds, joints, and areas prone to water pooling is essential. Number B, of regular inspection and maintenance is thickness monitoring, implement non-destructive testing, NDT, methods, such as ultrasonic thickness testing, to monitor the remaining wall thickness of critical boiler components over time. Number C, of regular inspection and maintenance is cleaning and maintenance, regularly clean condensate return lines and other equipment to remove sediment, scale, or corrosion products that may exacerbate corrosion issues. Number 7 is monitoring and control systems. Number A, of monitoring and control systems is automated control systems, deploy systems for continuous monitoring of water chemistry parameters, e.g., pH, conductivity, oxygen levels, with automated control mechanisms to optimize water chemistry. Number B, of monitoring and control systems is real-time data analysis, use data analytics and condition monitoring to predict potential corrosion issues and failures, allowing for proactive maintenance interventions. Number 8 is operator training and awareness. Number A of operator training and awareness is training programs. Train plant personnel on the causes and implications of boiler water condensate corrosion, as well as best practices for operation and maintenance. Number B of operator training and awareness is standard operating procedures. SOPs develop and implement standard operating procedures for water treatment, system monitoring, and maintenance activities to establish a routine focus on corrosion prevention. In conclusion, preventing and mitigating boiler water condensate corrosion requires a comprehensive approach that includes effective water treatment, proper system design, regular inspections, and proactive maintenance. By implementing these strategies, operators can significantly reduce the risk of corrosion-related issues, thereby enhancing the operational efficiency and longevity of boiler systems. Regular training and awareness among personnel also play a key role in sustaining these preventive measures. Boiler water condensate corrosion inspection monitoring based on API 571, Number A. Water analysis is the common monitoring tool used to assure that the various treatment systems are performing in a satisfactory manner. Parameters which can be monitored for signs of upset include the pH, conductivity, chlorine or residual biocide, and total dissolved solids to check for leaks in the form of organic compounds. Number B. There are no proactive inspection methods other than developing an appropriate program when problems such as a ruptured boiler tube or condensate leaks are recognized in the various parts of complex boiler water and condensate systems. Number C. Deaerator cracking problems can be evaluated offline at shutdowns by utilizing properly applied wet fluorescence magnetic particle inspection. Detecting boiler water condensate corrosion damage involves various inspection and monitoring methods that help identify corrosion issues before they lead to significant damage or failure. These methods can range from visual inspections to advanced non-destructive testing techniques. Here are some of the common methods used to detecting boiler water condensate corrosion damage. Number 1 is visual inspection. Visual inspection definition: regular visual evaluations of accessible boiler and condensate system surfaces. Visual inspection focus areas: inspect for signs of corrosion, rust, leaks, discoloration, pitting, and structural integrity of components such as pipes, tanks, and fittings. Visual inspection tools used: flashlights, mirrors, and magnifying glasses to access and examine hard-to-reach areas. Number 2 is thickness measurement. Thickness measurement using ultrasonic thickness testing or UT method. Ultrasonic thickness testing definition: a non-destructive testing method that uses ultrasonic waves to measure the thickness of materials. Ultrasonic thickness testing application: identifies thinning or loss of material in metal components due to corrosion. Ultrasonic thickness testing advantages: can measure remaining wall thickness without damaging the part. Thickness measurement using magnetic induction method. Magnetic induction definition: measures the thickness of non-ferrous or non-magnetic coatings on ferrous substrates. Magnetic induction usage: often used for coated surfaces to check for corrosion under the coating while ensuring the integrity of the underlying metal. Number 3 is corrosion rate monitoring. Corrosion rate monitoring using corrosion coupons. Corrosion coupons definition: small metal samples that are placed in the system and removed periodically to assess the extent of corrosion. Corrosion coupons usage: coupons are weighed before and after deployment to calculate the corrosion rate based on weight loss over time. Corrosion rate monitoring using electrical resistance probes. Electrical resistance probes definition: devices that measure the resistance of a metal to corrosion by monitoring the change in resistance due to loss of material. Electrical resistance probes application: often installed in areas prone to corrosion to provide continuous monitoring of corrosion rates in real time. Number 4 is electrochemical techniques. Electrochemical techniques using linear polarization resistance, or LPR. Linear polarization resistance definition: an electrochemical method that measures corrosion rates based on the potential change of a metal surface in a corrosive environment. Linear polarization resistance benefits: provides immediate information on corrosion rates and can be automated for real-time monitoring. Electrochemical techniques using potentiodynamic polarization. Potentiodynamic polarization definition measures the current response of a metal surface to changes in voltage, helpful in characterizing corrosion behavior. Potentiodynamic polarization application, often applied in laboratory settings for more detailed examination. Number 5 is borescope inspection. Borescope inspection definition, a visual inspection tool that uses a flexible tube equipped with a camera and light source to examine the interior of pipes and vessels. Borescope inspection application, ideal for examining hard-to-reach areas and identifying localized corrosion or pitting within the boiler system. Number 6 is pressure tests. Pressure tests using hydrostatic testing method, periodically testing pressure vessels and piping with water under pressure can help identify leaks and weaknesses that may develop due to corrosion. Pressure tests using pneumatic testing method, similar to hydrostatic tests but uses air or gas. This method can be riskier and requires careful management. Number 7 is leak detection systems. Leak detection systems using acoustic sensors, devices that can detect sounds associated with leaks in pipes or fittings, which could indicate corrosion-related failures. Leak detection systems using vibration analysis, systematic vibration monitoring can reveal issues like tubing wear or unexpected vibrations due to structural changes from corrosion. Number 8 is chemical analysis of condensate. Chemical analysis of condensate using water sampling. Regular sampling and analysis of condensate water can help identify pH levels, dissolved oxygen content, and other chemical parameters indicative of corrosion potential. Chemical analysis of condensate using laboratory analysis, analyzing for specific ions or compounds, like sulfates, chlorides, can also indicate potential corrosion issues. In conclusion, implementing a combination of these inspection and monitoring methods can provide a comprehensive overview of a boiler system's condition, particularly concerning water condensate corrosion. Regular monitoring and timely intervention can help prevent serious damage, thus prolonging the life of the boiler and maintaining operational efficiency. It is essential to establish a routine inspection schedule tailored to the specific system and conditions to effectively manage corrosion risks. Thank you.